Okay, so here is increasing and decreasing part 2. Okay. So remember that we have been working on deciding where we have critical values and where functions are increasing or decreasing. Now, we've been doing this by finding the derivative, which means they call this the first derivative test. So what we've been doing is the first derivative test. Okay, so let's do one more example before we move on to something a little bit different. So let's say that we wanted to discuss areas of increasing, decreasing, or maxes and mins, max, min, and the function they give us is x times the cube root of x minus 1. Okay, so remember that when it says discuss, really all that means you don't have to write a paragraph or anything. All that means is to make that little table. So we're going to look at making that little table. Now, I used this function here because this is one that most of us have no idea what this looks like, okay? I don't know what this looks like. So this is like, we really are going to figure out what's going on in this function. Now, remember that we need to see if there were any places where it's undefined or there's a discontinuity, but we're good to go with this guy. The cube root means that you can put negatives or positives in it. We're good to go. So I think the only thing that I'm going to do is rewrite this like that. Okay. And now this is going to require the product rule. Okay, so I want to do one that requires a little bit of extra work here. So let's go ahead and find the derivative. Okay, so take the derivative of the first, which is just 1, which is nice, and then leave the second. Plus, leave the first, take the derivative of the second. So bring down the 1/3, go x minus 1 to the, now that will be negative 2/3 power, and then we would multiply by the derivative of the inside with the chain rule, which is just 1, so luckily it doesn't affect us any. Okay, pretty all right so far? Okay, so what we end up with is the cube root of x minus 1 plus x over 3 times the cube root of x minus 1 squared. All right, now, like I said, I wanted to do a difficult one so that we would definitely have a difficult one to do. So remember to find those critical values. So for critical values, we're going to set it equal to 0. So we're going to set this guy equal to 0. I'm just going to take a shortcut and put 0 there. But yeah, this is no easy task for us. So in this case, I think we're going to need to find a common denominator, which means that we're going to need to come over here, and this guy is going to need a 3 and a cube root of x minus 1 squared. But again, that means up top we need a 3 and a cube root of x minus 1 squared. Okay, it's the same to top and bottom. So we have 0 equals. Now up top on this first fraction, we're going to have 3. And what I want you to notice is that here's the cube root of this guy squared, plus 1 more of them makes 3. So this actually cancels out the cube root, which actually makes our life a little bit prettier. So we have 3 and then x minus 1, and then we'll have this plus x, and this will all be over 3 times the cube root of x minus 1 squared. Okie dokie. So as I said, not the prettiest thing, but we're doing it. Okay. Now, remember that if there is a fraction, wherever that denominator is equal to 0, we have ourselves a critical value. So even though it's a cube root and squared and everything, if this is equal to 1, we're in trouble, aren't we? So we can say our first critical value is x is equal to 1. Now we can worry about the top. So if we distribute in, we'll say 3x minus 3 plus x will equal 0. So that gives us 4x minus 3 equals 0, which will give us an x of 3/4. All right, so we have just one more critical value, an x of 3/4. Okie dokie. So now, like we said, we want to make that table, make those intervals, and discuss whether we're increasing and decreasing, and decide whether we have minimums or maximums. Okay, so let's make our little table here. So we're going to go with the interval f prime of x, and then increasing / decreasing. I guess it doesn't need to be that big, but whatever. Okay, so we're going to go from negative infinity all the way up to 3/4. And then the next one is a real teeny one, 3/4 to 1. And then we go from 1 to infinity. Okay, so that's going to be kind of a crappy little guy right in there, but we'll figure it out. Okay, so in our first interval, all we need to do is take something negative. Okay, so you know what? 0 is in that interval, isn't it? So let's use 0. So if we plug 0 in up top, that'll be 0, that'll be 0. So if we go f prime of 0, we'll have 3 up top. No, we won't. Yes, we'll have -3, sorry. That guy goes away, but the 3 multiplies by the -1. So -3. On the bottom, we'll still have a 3. If we put in 0, this is going to be a cube root of a -1 squared, but it's squared, isn't it? So actually, this bottom is always going to be positive. So always positive. So it's just the fact that the top is a -3 means that the derivative on that interval is always going to be negative. Okay, now we got to do the kind of crappy one, the 3/4 to 1. So like a number that's in there might be like 7/8, okay, or even like 0.9. Maybe you want to do it with 0.9. Now here's the thing. Remember that this is always going to be positive, right? So do we care about it at all? It's not going to affect our derivative sign at all. So we could actually come up here and put in 0.9 right into this guy. So we could say, we want to do f prime of 0.9, but we're going to stick it right there. So we're going to go 4 times 0.9 minus 3. So that's 0.36 minus 3.6, sorry about that, minus 3, okay, which is going to stay positive, isn't it? And because we don't care what the answer is, we don't care what the denominator is doing. We just care that the sign is positive on that. Okay, now remember, never make any assumptions that it's then going to be positive again. We don't know that, or negative again, or whatever. So don't make any assumptions. So now let's put in maybe like the number 2. But again, we don't have to put it in down here. It's going to be positive down there. So if we come up here and we put in the number 2, 4 times 2 minus 3, that gives us a positive number as well, doesn't it? Okay, so we end up with a positive again. So that's your clue there, that it doesn't always go negative, positive, negative, positive. Okay. But that means we've got decreasing here, and then increasing, and then increasing again. So it's decreasing and then increasing and increasing. Okay, now remember, we also want to discuss whether we have minimums or maximums. So from at 3/4, on one side of 3/4, it's going down, decreasing, and then it turns and goes increasing, which means that we have a relative minimum at 3/4. Relative min at x equals 3/4. And then from at 1, we're increasing. Well, something happens, but then we continue to increase. So it's always increasing there. So even though something weird kind of happens right there, we're not changing from a min to a max or anything like that. So that's the only minimum or maximum that we have. That's the only extrema we have in this one, this 3/4. Okay, and the truth is, again, I'm not exactly sure what this graph looks like because, you know, it's been a while since I've really focused on graphing a lot. But the idea is just from this, I can get kind of a glance at what's going on. So we've got 3/4, and then right next to it we have 1. Now again, I don't know whether it's below the axis or above the axis or where it is, okay? But the idea is that wherever we want to make this, let's say that there's the minimum there, we're coming down like this, we're turning around, but then what happens is when we hit 1, let's say it's right there, when we hit 1, we don't turn around and go negative or go decreasing again. All we do is we change the shape. So you see how here we're going this way and then we go whoop. Now it's still increasing, right? Increasing, increasing, but the way it's increasing has changed, which makes this a critical value because something has happened. But it's not a minimum or a maximum. So here's the minimum and here's the critical value. And this stuff happens every once in a while. Now again, that's not necessarily what this function look like. I'm just giving you an example of what would have been going on here. Okay? Alrighty. So we talked about last time about how the relative maximums and minimums, they meant that the function was like as a maximum, it was bigger than everybody right around it. But we saw that there can be multiple relative mins and maxes, and they don't all have to be bigger than or smaller than each other. So that leads us to our next extrema, and we call those the absolute extrema. Absolute extrema. And then we say, 2 parts again, we say f of c is an absolute minimum if f of c is less than or equal to f of x for all x. Okay? And then it says f of c is an absolute minimum if f of c, oops, I just did minimum. Duh! Okay, sorry. Maximum, right? So f of c is an absolute maximum if f of c is greater than or equal to f of x for all x. Okay. All right, so with the absolute extreme, we're talking about that this value is the highest or the lowest value in the graph. Okay, so this one is not relative, it's not compared to the data or the graph around it, it's compared to the whole entire graph. Okay, so let's see here. What do I have in the way of examples? Okay, so this says, no, I don't like that example. Let me find another. Okay, example. Oh, okay, well apparently all your examples are gonna be like this. So, one more step before we do an example. We're gonna do, when we look for these absolute extremas, we're going to look at this on a closed interval. So absolute extremes on a closed interval. So that's what I didn't want to do the closed interval thing yet, but apparently it's there, so we might as well do it. So let me just give you an example here of without a closed interval. Okay, so when we look at our basic function, x squared, right? So we've got our nice parabola here, x squared. So would we all agree that there is a minimum there? Now, even further, can we agree that that is an absolute minimum? Is that the absolute smallest value that this graph has? So we would say an absolute minimum. Okay? But on this guy, is there going to be any absolute maximum? Okay? So the arrows imply that we're going up and up and up forever and ever. So because that's what we're doing, we're never going to have an absolute maximum. So the way that we can make sure that there is always an absolute minimum and an absolute maximum is by putting it on a closed interval. So what if I then said, use the interval, let's go, whoops, closed means not 1 to 2. So what that would mean is we're still going to have our same parabola, not 1, negative 1 to 2, sorry about that. But we're going to have negative 1 over there, and we'll have 2 over here, so 2, 4, 2, 4. Now, our parabola looks like that, because it cut off the rest of it, because we're looking at only at this interval. So now, when we look at this, do we still have an absolute minimum here? Still an absolute minimum here, absolute minimum. But because there's no arrow, because these end, do we end up with an absolute maximum? Okay? The absolute maximum is going to be here, isn't it? Okay, now the other thing is when you're talking about absolute minimums and absolute maximums, you want to make sure that you label it with the entire point. So this is going to be at 0, 0. This one would be at 2, 4. So before we've just been finding critical values and saying like x equals 2 or x equals 1. Okay, but now when it's absolutes, not only do we want to know the x value, we want to know the y value as well, because the y value tells you how big it gets or how small it gets. Okay, so that's the reason for the closed interval. On any closed interval, you will definitely have an absolute maximum and an absolute minimum. Okay? So now let's see what the example is that I have. And the nice thing about this is with everything that we have done, you don't ever need to graph anything, okay? You can do it all with the derivative. So it says find absolute extremes for f of x equals x cubed minus 12x, right, on the closed interval from 0 to 4. Okay, so this is actually easier than what we were doing before. So we need to find critical values, as always. So find critical values, which means that we need to take the derivative. Okay, so we'll go f prime of x here is 3x squared minus 12. Everybody agree? Okay. And then we will set that equal to 0. So we end up with x squared equals 4. We've got a nice b here on the board. And x is going to equal, don't forget the plus or minus 2 when we take the square root. Look good to everybody? Okay. Now here's the dealio though. There are two critical values there, aren't there? How many of them are we interested in though? Because is the negative 2 in this interval? It's not, is it? So we don't care about the negative 2. It is a critical value, but it's not a critical value that affects us. So we only need x equals positive 2. Now, remember we're looking for critical values, so these 2 points also become critical values. So we also have x equals 0 and x equals 4. So remember, come back to this. This guy was a critical value, right? There weren't any other critical values until we put a cap on it, and then all of a sudden we had 2 more critical values, didn't we? Okay, now, again, we don't need to graph anything, we don't need to do anything. All we need to do is plug each one of these guys back into the original function to see what the answer is. Okay, so we need to find f of 2. Okay, not f prime, not here, here. Okay, so if we go f of 2, that's going to be 8 minus 24, right? Everybody agree? Which will give us negative 16. Then we're going to find f of 0. Well, if we plug 0 back into the original, we just get 0. And then we're going to find f of 4. Okay, so if we plug 4 back into the original, we get 64 minus 48. say 64 minus 48, which gives us a positive 16. Good to everybody? Okay, so we know what the values are at each of our critical values. Now the lowest value is going to be the absolute min. The highest value is going to be the absolute max. So we can finish this off by saying that guy looks lowest, so we're going to say the point 2, negative 16 is an absolute min, and the point 4, positive 16 is an absolute max. All right, look good? And again, we don't really care what's going on in the graph, especially like if we were in regular calculus class, we would. But for us, it's more of these critical values that are going to be important to us. So let me show you an example here. I'm going to turn the page in my book, so let me find an example. Here we go. All right, so I can erase this. Okie dokie. So, McDonald's profit function for selling X burgers is P of X, whatever, equals 2.44x minus x squared over 20,000 minus 5,000 on 0 to 50,000. Find the sales level that maxes out profit. So this is more of an example that you would be doing, and this is definitely a valid example. So McDonald's is producing X burgers, and this happens to be their profit function. Okay, now here's that closed interval. It says that this is for X between 0 and 50,000, and that should be a bracket and not parentheses, I apologize. So the idea is that McDonald's can't just produce an infinite number of burgers in, let's say, a month. There's only a certain number. So they know that they can go between 0, right? They could produce none. And 50,000 is about the max that they can supply. So they want to know where the sweet spot is, where their profit will be maximized, okay? Excuse me, so that's going to be an absolute max that we're looking for. So we already have these two, but we need to find the derivative of this guy. So we'll go F, that is not an F. I don't know what's wrong with me this morning, I apologize. So P prime of X. So derivative here will be 2.44 minus, if we bring the 2 down here, it will cancel with that one, and it's just going to leave us X over 10,000. Right? And that's our derivative then. Okay, so in order to figure out our critical values, we've got to set this guy equal to 0. So we'll go 2.44 minus X over 10,000 equals 0. So we have 2.44 equals X over 10,000. And that will give us X is equal to, what, move the decimal place over 4 units? So 24400. Okay, now, it's early in the morning for me, so let me just check that just to make sure I got my right number of zeros, because I'd hate to screw up, but yes, okay, just checking. Okay, so we've got 24,400. Now, we also had, that's a critical value, we also had a critical value of 0 and a critical value of 50,000. Okay, now we have to plug all three in there, okay, to figure out which one is the maximum. So now remember, we're plugging back into the original, So we go the 24,400. Oh, all right, well, this is definitely time for your calculator. 24,400. So 4 times 24,400 minus 24,400 squared divided by 20,000 minus 5,000. Okay, so here I got 2, 4, 7, 6, 8, and this would be in dollars. Okie dokie. Let's say that they were to produce 0. That one's nice because that'll fall out, and it will be equal to negative $5,000. So can we agree that McDonald's should produce more than 0 hamburgers? It's not going to work well, is it? Okay. And then the last one would be the 50,000. Okie dokie. So 2.44 times 50,000. That's too many zeros. Minus 50,000 squared divided by 20,000 minus 5,000. And here I got a negative $8,000. Okay, so we've got our three numbers. Remember, we're looking for the absolute maximum, which is definitely going to be this guy, isn't it? So we know if they produce 0 burgers, they're not going to be making a profit. Okay, they're just not going to work. Okay, so that was negative. But actually what we find out is if they overproduce and they produce 50,000 burgers, it didn't give us a time unit, so I don't know if this is like in a week or how many burgers people actually eat. So, but at 50,000, we're actually at negative 8,000. So what we're noticing here is that profit falls off if they overproduce. So the sweet spot happens to be 24,400 burgers. Okay, so it said find the sales level that will max profit. Now in that case, the sales level is the 24,400 burgers. Okay, so that's the answer to this question. If I then also said, what is the profit? That's when we would say $24,768. Okay, so sales level is 24,400. Sales profit is $24,768. Okay, look good to everybody? Okay, so remember when you're finding the relatives, that's where you're looking at the increasing and decreasing, so relative mins and maxes. And when you're doing the absolutes, you're finding your critical values, and then you're just plugging each one into the original function to see which one's bigger and which one's smaller. Okay. Alrighty, so that does it for 3.1 and 3.2.